Hello, and welcome to another lecture in my series of historic surveying and mapping. This session is about the plane table. This is a unique device that I think is not portrayed nearly enough by modern reenactors. Uh, it has some very uh, interesting uses and applications that make this a particularly well fit device that was known and was used a great bit. And I agree totally with what William Laybourne describes in The Complete Surveyor of 1674, where he describes the plane table, how it was made, how it's altered, and it being the most absolute instrument of any other for the surveyor to use, in that it performeth whatsoever may be done by either the theodolite, circumferentor, proactor, perambler, or any other graduated instrument, with the same ease and exactness. I hope you'll enjoy these various uses and mysteries of the plane table. We'll begin with a little bit of history. I did some research back to when this device was first being discussed in literature, and it really comes back to the mid 16th century. The first English mention that I could find of this particular device was near the end of that century, 1590, and the device has been used well into the 20th century, making it a very long-lived, very useful device that actually has changed some in how it has been discussed and treated over time. Prior to the early 19th century, the device was referred to as the plain, Plain table, meaning unadorned, simple, easy to use. And it was only later in the 19th century that the definition or usage of the name really changed to the Plane, referring to the fact that we use it as a extended surface parallel to the Earth that we're measuring. The plane table has many advantages in that it can be used all the way from very small areas, actually inside of a building or a room, to outside as far as the naked eye can see, or of a telescopic alidade, we'll discuss that later on, where we aid the eye, it can go much further. So it's as far as we can see. So we can do very large regional mapping, and we'll even look at how we can extend multiple sheets of paper to get very, very large areas, as well as the very small areas. So it's suitable in many different ways, but it also has the very tactile advantage of building a map as we go. So it's not just taking measurements being written down in a field book, but we're actually collecting data points that are referenced to each other on the map. And in many cases, connecting those points to actually build the map as we go. And we can see the map progress as we collect the data, which also gives us the advantage of understanding of when something may be going wrong in the map. Things that we don't see when we're using a field book to collect data, and we don't see that until we the mapping phase, which will be a whole nother lecture that I want to get into. It also has the advantage because once the table is set up, we can do a lot of mapping without moving the table and not having to reorient that particular device. And so in areas that have high iron deposits or other sort of magnetic anomalies, where moving a device from point to point is going to affect the needle. We don't have that disadvantage with this particular device. It also doesn't take a lot of training or a lot of skill for many of the uses of the device, and we're going to talk about the many ways it can be used. And the other advantage is that it is generally a fairly inexpensive device. They may be difficult today, certainly finding an extant plane table to use. Even just the frame are very, very expensive, but they can be built very easily or relatively easily as well. Certainly doesn't require all the brass of a circumferentor or many of the other devices that we might use, theodolites and such. So in relative terms, it is fairly inexpensive and fairly easy to use. When we look at the construction of the table, I have looked at many historic examples, and while sizes vary by a couple of inches in any direction, the average that I've been seeing throughout the 18th century examples is roughly 13 inches by 15 inches. So some are more square, some a little bit more rectangular, but it's roughly that size. In addition to the table, we also need to raise it from the ground. We use a three-legged staff for that. Again, the term tripod is not one that was known in the 18th century. It's a much newer term. But a three-legged staff, usually with a brass ball adapter on the top that allows us to change the table because the legs at that time of the three-legged staff were not adjustable other than splaying one out more so than the others. That can affect stability, but we can set the table very strongly and then adjust the adapter to make the plane of the table equal to the plane of the earth that we're mapping, even though, again, we're not looking at it as the plane plane table. It is important that the table be level with the ground. The table is also made with a frame. This frame can be collapsible, as most of the extant examples that I've seen, but this frame, the important thing is that it is graduated. It is graduated in relation to a point at the center or off center of the table. We'll look at different examples of that so that it can be used in many different ways. The photo at the bottom shows that the frame actually overhangs just a little bit over the table itself because the frame not only holds the graduation, it also literally holds the paper to the table. So the paper needs to be larger than the size of the frame. It's laid out on the surface, and then the frame actually crimps it onto a rebate that goes around the table, a lip, that, if you will, around the edge of the table that is recessed. So the frame actually pinches that paper to the table and keeps it stable to be used. If the frame were the same width as the table, it'd be very difficult to get your fingernails in there and try to pull it up. So that's why the frame usually overhangs the table a little bit to make it much easier to pull that frame off. We also need some sort of an alidade. This is commonly an open sight device. It's going to have a long fiducial edge that should be very straight and may or may not be in line with, but actually related to the sight vanes at either end. So this is an open sight vane in this case, where we have the very small slit that we have to put our eye very close to look through the open at the other end that may have a hair across that to help us sight to whatever our object is. That's what ensures that our eye is in line with that edge of our index. We'll look at some other examples of this as well as we go along. Here's one of those, and that is a telescopic alidade. So in this case, that fiducial edge you'll see is along the bottom, that straight part of the brass, and then the alidade is a telescope on top of that. Grinding the lenses for telescopes was very difficult in the 18th century, and so what you'd find is a minimum number of lenses, which unfortunately often flipped or inverted the image. So when you look through a telescope, you didn't see ground normally below. It flipped it around so that the ground was actually up and the sky was below. This is one of the ways that you can tell an 18th century telescopic device because of that inversion that happened. When lenses became easier to grind, they added additional lenses which would then re-invert the image. So that's typically going to be a later or certainly a more expensive telescope. In addition, we also need a needle box, or a compass. This particular compass has a dovetail that allows it to be slid into the table so it appears in the same position so that we can orient the table in the same way each time. Some needle boxes may not have a full 360 degrees of freedom for the needle, but yet a small trough that only gives maybe 5 or 10 degrees of freedom to the needle, because all we're trying to do is orient north. We're not looking for our degrees off of this particular compass. It's simply for orienting the table. We also, in most cases, will need a pair of dividers. Dividers usually are brass. They can be made of different materials. The tips are usually iron, so they can be sharpened. We need sharp points, um, not only for pricking the table or for pricking the paper, but also for making very precise measurements against our scale. So the dividers should have good points to them and should move freely, but not easily. The divider should be able to be opened and left in a position and moved from the paper to a scale or back again. We also need a plane scale to work against, some form of ruler or scale. We'll look at how we use those as well. And then a pencil holder or a porte crayon, which is a way of holding our lead so that we can draw on our paper. Remember, we're actually building the map as we collect our data. Some of the common uses of the plane table, as we see here in this drawing, F, we see the three-legged staff. It's hard to see the adapter because of the way the table is leaning, but we see the table with the graduated frame. We also see the needle box or compass set into the dovetail, and then we see some form of a alidade. It may be wood, it may be brass, um, but something that allows us to sight along the edge. That set of tools right there allows us to perform the same tasks as the theodolite, the circumferentor. We see a surveyor's compass there, G, also known as a circumferentor, typically made of brass. The drawing here certainly would indicate one being made of brass because it has very little material there holding the sight vanes, but a very large dial in the middle. The reason is that the larger the dial, the more accurate the readings we can get. So as the dial size increases, the distance between each of the 360 degrees increases, which gives us a better ability to estimate the number of minutes, those 60 minutes in between each of those degrees, which really are typically broken down to the nearest 15 minutes. So the first quarter, half, third quarter, or all the way to the next degree. A semicircumferentor or a semicircle is a device much like the circumferentor, except that it doesn't have all 360 degrees. It only has 180 degrees. But the advantage of having just 180 degrees, although we can't measure in all directions, we can reorient north to south or south to north to get the angle that we're looking for within that 180 degrees, but typically allows us to make a larger effective dial without having to have the entire dial on one device. And so it's another way to increase our accuracy. And we'll also look at how we use the plane table as a resection device. Now let us look at the specific uses of the plane table, specifically here as a theodolite or a semicircumferentor or semicircle. We have here in figure 1 an angle represented by EK and KG. We can measure this by placing the plane table at the center point of that angle, so at position K. By using the center point of the paper or some point on that paper to represent K, we can place our alidade along that line from K viewing point E through the sight vanes of the alidade, and then simply draw along that edge of the alidade to represent the same line KG, KE on the ground, onto our piece of paper. Now by moving the alidade with the same point K along the edge of the alidade, but now viewing to point G, we have that angle represented. And if we scribe a line along that fiducial edge, we now have a representation of the same angle on the ground, EKG, on our piece of paper as well. We'll look later on at how we scale that to get a full scale drawing, but if all we're looking at is the angle represented, we now have that measured and already drawn. Now, if we extend the idea of drawing a larger area, so here we have part of a field, polygon represented by A, B, C, D, and so forth. If we were to use a circumferentor, what we would do is move that device along each of those stations. So starting at station A, we would orient the device looking from A toward B, and the needle will actually be pointing north and referencing the angle from north to the line AB. And then we would write that down and measure the distance, and then move on to station B, looking forward to station C to get that angle from north, and write all these notes down into the field notebook. When we use the circumferentor instead, in the same way, by placing the device at station A with a piece of paper pinched into the board, we can now pick a point on that surface to represent station A, looking ahead at the size of the area that we're going to be drawing, taking that into consideration. Now we draw that point A, set our alidade looking to point B with the edge resting on point A on the map. We can then scribe that line. We'll come back to how we scale that line a little bit later on. But for right now, we have that angle defined on the board itself. So we've drawn it to the map. Now, as we pick the table up and move it to station B, we could go ahead and orient again to north using our needle box, but we also have the ability to sight back to station A and move the table with the alidade already laid against that line so that the table is oriented back to that position. So whether that agrees with the north position that we had or not, it is now in relation to the same way that it was at station A. Now that we have backsighted, we can look forward to station C by placing the edge of the alidade at point B and scribing a line forward. Now we pick the device up and move it to station C, and allowing that end of the line, which we would have scaled to represent point C, and place our alidade from point C looking toward point D on the ground after backsighting. Now we sight forward, draw our line, scale that, so now we have point D. Now we can pick the entire table up yet again, sight backward to point C so that we have the orientation of our table, and then can go ahead and continue drawing forward to the next point. Now we see here one of the issues that we have with a plane table, and the scale of map that we can draw will be related to the size of the paper, at least using one sheet. We can get around this, however, by using multiple sheets. So we can do that, and we have the representation of A, B, C, D here on the right side of the screen. And we have added a north line that intersects line DE at point O. Point O then becomes our overlap line that we can then use for a second piece of paper that is also oriented to north. And then along that line DE, we have point O, and we will orient the board looking back to D, looking forward to E, drawing the line, and then continuing on as we did before. Once we get to point G, we can cite back to point A once again. And now we have a second page that can overlap the first page and hopefully be able to close this parcel of land that we have. And we can go across multiple sheets if we need to, if we want to do a very large area at a very detailed scale. This does bring up one of the potential issues with a plane table, and that is going to be the error of closure. So as we work with the plane table and constantly move it from station to station, we are having to align the top of that table so that it is parallel with the ground. So it's at a horizontal plane. This can be difficult to do, and in the drawing here, it actually gives that appearance that the table may be slanted. But if that were slightly different between different stations, just off from horizontal, we then will have a very different distance and potentially a different angle as we draw in each of those locations. So the description here from William Gardner is that plane table surveyors, when they find that their work does not close correctly, does not come back to the beginning point the way that it should, they often might close it wrong, not only to save time and labor, but also save them having to acknowledge the error to their assistants so that they might lose some faith with their assistants. But the problem is that they may not be within their power to even be able to amend that drawing and to do the proper closure because the line distances and the angles may be different because the table is at a slightly different plane. The mathematics are much more difficult. And so it may not be, as William writes here, the fault of the instrument rather than the surveyor, or the uneven land and where the table can't at all stations be set horizontal or in one plane consistent between all those, so that it's impossible that the work should be true in all of its individual parts. So that is a potential issue. The other issue is the paper itself. So there is a great inconveniency of the plane table in that the paper itself can render it impractical in moist weather. I know in the South here, we deal with a lot of humidity. Here, Chambers is saying that even the dew of the morning and the evening is found to swell the paper considerably and of a consequence stretch and distort the work, which can be different depending on the thickness of the paper throughout if it's not absolutely consistent. The other thing that I found is in resting my hand on the paper for a long time, particularly my cupped palm, because my palms have a lot more moisture in them. And so the paper can absorb that and actually stretch differently where my hand might be cupped over the paper for a long time versus those areas that the sun might be hitting and having it dried out. So the fact that we're using paper means that the instrument is not useful in all types of weather. So the solution is to simply leave off the paper and setting a pin at the center instead and use it in the same way that we would use a theodolite or a semicircle or a circumferentor. So what we're talking about here, and if we look at a simplistic view of the board, here we see the outer frame with the graduations around it, and we see that center point. That's going to be a very fine point in the middle of the board, usually protected by a piece of brass or a piece of ivory or bone, something that's going to be able to keep that point from stretching or getting larger. We want that to be a very fine point because that reference point is where all of these graduations around the frame come from. So when we look at the frame directly to the top and directly to the bottom, we see that the reference lines pass through that point. Same thing looking left and right. And then between the horizontal to the vertical, we see the line having to change angle as we go throughout. Because although we're looking at a square, we're trying to read the angles around the compass as we do this. So when we use the circumferentor, we need to place a pin or the leg of our divider into that hole at the center and bring the fiducial edge, that's the edge that we're drawing against of the alidade, up against that center point so that it becomes the pivot point for moving the entire alidade. Now we'll look through the sight veins, which I haven't drawn here, but we'll sight down that alidade to our next station, wherever it is we're looking at. Now, if it's up against that center point, that means that we can read off of one side of the frame or the other the angle that we're looking to, and the angle at the opposite end of the frame will be the complementary angle to what we're looking at. So we have a bit of check and balance here using it as a circumferentor. The other advantage here is that while a brass or even a wood circumferentor might have a large dial size of 6 or let's even say 8 inches, that would be a huge dial. The effective diameter of the dial in this case, with a board that's say 13 by 15 inches, is going to be somewhere upward of 14 inches around that center point, or even greater than 15 inches in some places. So what that means is that the lines between each degree are separated much more. And so it makes it easier to interpret those 60 minutes between each degree, which really we tend to look at it just as quarters of a degree or 15 minutes. So is it the first quarter, half, or the third quarter, or is it all the way at the next degree? But having more distance between those points allows us more precision in our measurement. We can make that even better by using the table in the same way that we would use a semicircumferentor. So in this case, the table has yet another point. Again, another piece of brass or something to hold that point. And the frame has two sides. So one side is indexed to the center. And now when we flip the frame over, we notice that the other frame is now indexed to that second point that's somewhere about a third to a quarter of the way into the table. So now that vertical center line is at that third or quarter mark, and the separation of the degrees is even greater on the right-hand side, excuse me, of the board. So as you bring our alidade up to that pivot point, we'll be able to read very fine degrees to the right-hand side, far less to the left because the effective diameter will be much less to the left side than it is to the right side. So now we've taken what may have been 15-degree effective diameter and increased that to 20 inches. So a far greater precision than what we would be able to get from either a circumferentor or even a semicircumferentor by using the plane table. So using it in the field in this way, here we have a six-sided field referenced by A, B, C, D, E, F, and then we see our north-south line running through the middle horizontally. And then we have point L in the middle of the field. If we place our board there and allow the center point of the plane table to represent the center point of that field, we can use that center point, align our alidade, and sight from the center of the board out to point A. Now, we haven't really talked about scaling yet, and that's going to be part of another lecture, but we can send out our chainmen to go ahead and measure what that distance is from the center of the board, where we're measuring from, out to station A in a straight line. Once they give us that measurement, we can then take a scale and our dividers and set the number of chains and links to the reference scale on our divider, and then take that number and move the one leg of the divider to the center point of the board, and then use the other leg to actually prick the paper along line A to get the exact location of point A on the field represented on our paper at a specific scale. Now we do the same thing to point B. So placing our alidade along the center point, we can scribe a construction line going out toward point B, have our chainmen go out and take the measurement, bring that measurement back to us, set the divider to the number of chains and links, and then move the leg of that divider to our center point, prick the other side of the construction line B to where point B is, and now we have points A and point B in relation to each other without having to move the device at all. We can continue to do this throughout the other stations all the way around and then simply connect all the dots. And now we have a scaled, complete drawing of our six-sided field. Let's make it even more complex. So in this case, we might have two fields, a pasture and a woodland, or two different pastures that we have here. What we need is a point that we can see all the other points from. And it may be in certain cases that we can't see all the points of the field from any one given location. So we'll go to the southern part of this drawing in that smaller field and place our plane table in the middle of that field and then sight out to all of those other locations. Now we have the angles that represent out to those points. And if we have someone measure the distance from that center point out to each of those points, we can then scale that part of the drawing. Now, before we move the table, we can sight out to one more point, and that would be the next station that we want to move the board to. And so we'll scribe that construction line, measure the distance, pick the board up, move it back to that location, sight back to our original station so that we have the exact same orientation without having to worry about any sort of magnetic anomalies or reorienting the board with a box needle. Now we have our new location in reference to the previous location, and we can sight out to each of those lines again. One last application is to use the plane table as a resection device. So in this case, we might want to know the distance from a windmill, point A, to the corner of a church at point B. And in this case, due to the river, we may not be able to get across to actually measure either the angle or the distance from point A to point B. However, on our side of the river, we can know the distance and angle from point C to point D. And so using a process of resection, we'll be able to infer A and B. So placing the table at point C, we will pick a point to represent point C on the table. Using the leg of our divider or some pin on the table to set the point, we'll place our alidade along that line and scribe the angle from C to A. We'll do the same thing from C to B. So we sight our alidade, draw the line. We don't have that ability to go and measure line CA or CB to be able to scale them. All we have is the angle. However, if we also draw a line from C to D by sighting that, and then moving the table over to point D, back sighting to make sure that we have that in alignment, now we can go ahead and make the measurement from D to A and also from D to B. And because we know the distance from C to D, we also have the angle drawn to the map. The points where the two angled lines intersect will represent point A and point B. And so now we can actually measure on the map itself and then work our dividers back to the scale to determine what the actual distance is between points A and B. But these are just some of the ways that we can use the plane table. And I hope, if nothing else, it's inspired you to learn a little bit more about a really wonderful device.